Hello, welcome to Electrical Engineering Made Intuitive.
Hello everyone. With that introduction, let's start doing this homework number 417 in the book. So what I'm going to do is to try and solve this doing all three different methods. We're going to start with our favorite method, or at least my favorite method, the universal, and then move on to nodal, and finally finish with the mesh analysis. Okay, so the algorithm, we're going to start by identifying all nodes. So this is one node, and I'm going to assume that's my ground. This is another node. This is another node. This is another node. Finally, this is another node. Now, when I label the nodes, I'm going to use my knowledge of equations for sources and label this node as 160 volts. For those of you who are still not ready for this, what I'm doing is that I'm saying in my head that this is V1, and then write the equation for this component, which is V1 minus 0 is equal to 160, and at that point I just put it up there. Then I'm going to call this V1, and I'm going to call this one V2, and finally call this one V3. Then for the currents, I'll pick this current as I1, write the KCL for that node, and immediately call also this one I1. This one already has a name, I'm not going to change it. This label is being utilized for this dependent voltage source, so I'm not going to touch that. Then I'm going to take this current as being I2 and write the KCL for that node, and assume this current also basically realize that this current is also I2. Doing KCL for that node is going to give me the same information, and therefore I'm going to call that also I2. So with that in mind, I am done with labeling the circuit. I'm going to move on to writing KCL and equations for components. In order to do KCL, I realized that I have 1, 2, 3, 4 nodes. I don't need to do KCL for this one, nor this one, and finally not even for that one. So, and I'll never do it for ground anyway, and therefore there's only one node that I need to write the KCL for. I'm going to add up all the currents that are going into that node, node V1, and those are I1, I2, and I sigma. So I'm going to add them up. I1 plus I2 plus I sigma, and then add up all the currents that are leaving that node, and that's 0. There's no current that is leaving that node. Then I'm going to move on to equations for components. So the number of components are 1, 2, 3, 4, 5, 6. I took care of the equation for this component when I called that node 160 volts. And therefore there are 5 components for which I have to write the equation. So for the 10 ohm resistor, I1 is equal to 160 minus V1 divided by 10. For the 30 ohm, I2 is equal to V2 minus V1 divided by 30. For the 20 ohm, I have I2 that's equal to 0 minus V3 divided by 20. And finally for the 100 ohm, I have I sigma equal to 0 minus V1 divided by 100. That takes care of all the resistors, and the only component that is left is the dependent voltage source. So the potential of the positive terminal, V2, minus the potential of the negative terminal, V3 is equal to 150 I sigma. So let's count the number of unknowns. We have 1, 2, 3 unknown voltages, and then 1, 2, 3 unknown currents, so total of 6 unknowns. And as you can see, we have a total of 6 equations, and that means that we should be able to relatively easily find values for all of these. So as we discussed, there are different ways to do this. Let's start with doing it just kind of haphazardly, the process of elimination. I'm gonna take these two equations and put I sigma as minus V1 divided by 100. So from these two, I'm going to get V2 minus V3 is equal to minus 150 V1 divided by 100, and that is minus 1.5 V1. So with that, I can actually write V2 or V3 as a function of V1 and the other one. I can equate these two to each other, and that gives me V2 minus V1 divided by 30 is equal to minus V3 divided by 20. If I multiply both sides of this by 60, that gives me 2V2 minus 2V1 is equal to minus 3V3. So from these two equations, I should be able to write both V2 and V3 as a function of V1. So let's try to do that. For example, from this one, I can take V2 and put it in the other one. So from this one, V2 is basically V3 minus 1.5 V1. So I'm going to replace that there. So 2 times, instead of V2, I write V3 minus 1.5 V1 minus 2 times V1 is equal to minus 3 V3. So now I'll move things around. So 2 times V3 plus 3 times V3 is equal to 2 times V1 plus 3 times V1. So from this, I actually clearly see that V1 and V3 are the same. So that given, I can put this result back in here. So V2 minus V1 is equal to minus 1.5 V1, from which I can clearly see that V2 is equal to minus 0.5 V1. So from these two, now I can take all the current values and put them in the KCL and write all the current values also as a function of V1. So I get one equation with one unknown. So I1, I'm going to replace it with the first equation for components. So 160 minus V1 divided by 10. I'm writing the KCL. Plus I2 is minus V3 divided by 20. And I know V3 and V1 are the same. So that would be minus V1 divided by 20. And finally plus I sigma, and I sigma is actually minus V1 divided by 100. So minus V1 divided by 100. That's all equal to 0. This is giving me one equation with one unknown being V1. So I multiply everything by 100. That would be 1600 minus 10 V1 minus 5 V1 minus V1 is equal to 0. Move everything to the other side. 16 V1 is equal to 1600, and therefore V1 is equal to 100, as you can see, 100 volts. As soon as I get that, V3 is also 100 volts, and then V2 is equal to minus 50 volts. That concludes this, because now I can put it back in here and calculate any currents. So we're done with this first method of solving this equation. Now, this was using just process of elimination. You can do this any other way. You can move everything around, write the matrix, and do it that way. You can also, if you have a good calculator, just punch in all these equations and it gives you everything that you need. Okay, let's now move on to the second method, which is nodal analysis. So let's just multiply the first equation to 300. I'm going to get 30 V1 minus 4800 plus 10 V1 minus 10 V2 plus 3 V1 equal to 0. Multiply by 60 for the second equation. That would give me 2 times V2 minus 2 times V1 plus 3 times V3 is equal to 0. And then finally 1.5 V1 plus V2 minus V3 is equal to 0. So let's just rewrite these to prepare them for the matrix. So 30 plus 10 plus 3, 43 V1 minus 10 V2, it's equal to 4800. For the second equation, minus 2 V1 plus 2 V2 plus 3 V3 is equal to 0. Finally, 1.5 V1 plus V2 minus V3 is equal to 0. So the matrix form turns out to be 43 minus 10, 0, minus 2, 2, 3, 1.5, 1, minus 1, multiplied by V1, V2, V3. That's equal to matrix of knowns. This vector. So now you take this matrix, inverse it, multiply it by this vector, and it gives you V1, V2, and V3. Just to check a sanity check, we know V1 from the other method that we did. We know V1, V3 are 100 and V2 is minus 50. You quickly put it here, you can actually see that that's correct. So that's 43 times 100 is 4300 minus 500 minus 500, which would be 4800. So you can see that those results actually fit in this equation. So obviously that you're going to get the same results for the same circuit. Assuming, just keep in mind, this is assuming that you have used the same ground. If you change the ground, your reference, then the voltages might, the potentials are going to end up being different. Okay, so with that, we're going to move on to the last way of doing it. Okay, for the last method, we're going to do mesh analysis, and as we discussed for this one, we're not going to identify nodes. Instead, we're going to identify loops, and there are two obvious loops here. So there's this loop, and there's this loop, and I'm going to intentionally pick the currents to be reverse of each other. Like I said, this is arbitrary, so I1 and I2. Then you go through the loops, start from a node, and then add, subtract voltages. And once you go back to the same node, then it's obviously equal to 0. So every time the potential increases, I'm going to add. Every time potential decreases, I'm going to subtract. This is a convention. You can do exactly the opposite. As long as you're consistent, that should work. So starting from this node down here, 160 minus 10 times I1, which is the voltage difference across the 10 ohm law, minus 100 times the current passing through the 100 is both of these currents added to each other. So that would be I1 plus I2, and that's equal to 0. For the other node, I'm going to start from this node down there, 150 times I sigma minus 30 divided minus 30 times, sorry, minus 30 times I2 minus 100 times again I2, I1 plus I2 minus 20 times I2 is equal to 0. And then since we have two equations, we have to actually define what I sigma is, so that we get two equations, two unknown, and I sigma obviously in this case is the negative of I1 and I2 added to each other. So with that, I'm going to rewrite this. We have minus 10 I1 and minus 100, so minus 110 I1 and minus 100 I2. That's equal to minus 160. For the second equation, let's quickly rewrite this one. That would be minus 150 I1 minus 150 I2 minus 30 I2, and then another minus 100 I1 minus 100 I2 minus 200 I2 is equal to 0. So we go here, minus 150 minus 100, that would be minus 250 I1 minus 150 here. Another, sorry, this is 20. Another minus 50, that would be minus 200. And then with this, minus 300. So minus 300 I2 is equal to 0. So from this one, we have I2 equal to minus 250 divided by 300 I1, which is minus 5 divided by 6 I1. And then you put that here. So that would be minus 110 I1 plus 500 divided by 6 I2. No, sorry, I1 is equal to minus 160. And that actually is going to tell you that I1 is equal to 6, I think. So let's try that. Yes, so this I1 is 6, you put it here, and I2 is minus 5 amp. So now with these two, you can calculate all the voltages across the components. Keep in mind that once you calculate any of these are the voltages across the components. For example, if you take I1 and calculate this voltage across the 10 ohm, that would be 10 times 6, which is 60. That's not this voltage nor that voltage, is the voltage difference. And if you recall, this potential, assuming that you take this one as ground, turned out to be 100, and this being 160 gives you a 60 volts difference using the other two methods. So these results are all compatible, consistent with each other. And the currents that you calculate using these are going to all turn out to be exactly the same. The value for potentials are different depending on where you choose your ground, but the currents are going to have to be the same. So okay, with that I'm going to finish this, and I'm going to prepare another video on analyzing the same circuit using the circuit analysis tool that I introduced to you, so that you get some practice with it and see how easy it is to actually check your work using circuit analysis tools. Thank you for your attention.